Hey guys, I hope you're all doing good. Welcome to another new video. In this particular video, I'm going to teach you how to write programs for simulating an air standard cycle. As you know, air standard cycles are quite important. They help us understand the theoretical limits of a particular cycle, which can be used to get an idea about performance of real-world systems like IC engines or gas turbines. In this particular case, we are going to be writing a program that actually simulates. Now, the concepts that we will be employing to solve the Otto cycle can be used for any other cycle, which means once you have completed this program, you will be able to write code to solve any other air standard cycle that you want. So this is how the PV diagram for an Otto cycle is going to look like. So the process 1 to 2 is going to be isentropic compression, 2 to 3 is going to be constant volume heat addition, 3 to 4 is isentropic expansion, and finally 4 to 1 is going to be constant volume heat rejection. So now let us talk about the inputs that are typically used to solve this problem. So typically the volume at state number 1 is provided as an input, which is V1. And then the temperature at state number 1, and with these two information, the pressure at state number 1 can be calculated. All right. And the other input that is typically provided is the compression ratio. Okay, so once we know compression ratio, we can actually calculate V2. So once we have V2, we should be able to calculate P2. And once we have P2 and V2, we should be able to calculate T2. Usually in these type of problems, the temperature after combustion occurs is specified, which means either T3 is provided or P3 is provided. So in this case, we are going to assume that T3 is provided. All right. So if T3 is known, then what we can actually do is we can calculate V3, because V2 and V3 are going to be same because of constant volume heat addition. And once V3 is known, T3 is known, P3 can also be calculated. All right. The same concepts can be applied and we can determine the values for state number 4. And once we have all that information, we will be able to compute the 4 points in our PV diagram. Now, in order to construct the PV diagram completely, we need to know how the volume changes from state 1 to state 2. Now, this actually depends on the engine kinematics. So what we are going to be doing in this particular problem is, instead of starting from V1, we are going to be starting from the engine geometric parameters. So once we have these parameters, we will be able to solve the kinematics equation of a piston, and we will be able to compute the volume trace. From this volume trace, we will be able to calculate our swept volume and clearance volume, which is the information that we require to calculate V1 and V2. All right. So let us get started with the computer program. All right. So the first thing I'm going to do is create a new file in Matlab, and then I'm going to start with clear all, close all, and CLC. So once this is done, I need to define the variables for state number 1. Okay, I'm going to say that the pressure at state 1 is 1 atmosphere and the temperature is 500 Kelvin. So for state 1, the volume will be computed using the geometric parameters of the engine. So let us first input that. I'm going to be assigning values for the bore, the stroke, the connecting rod length, and the compression ratio. All right, now we are set to calculate the swept volume and the clearance volume. The swept volume is basically the volume of cylinder that is defined by the bore and stroke, and hence that is equal to just pi by 4 d square times L. And the clearance volume is nothing but the swept volume divided by compression ratio minus 1. The total volume, which is basically the swept volume plus clearance volume, is equal to V1. And V2 is nothing but the volume at the top dead center, which is nothing but the clearance volume. So now if you actually take a look at the program, the state variables for state point number 1 have already been computed. Now let us calculate the state variables for state number 2. Now the pressure in state 2 can be computed using the relation P1 V1 power gamma is equal to P2 V2 power gamma, which defines the isentropic compression process. So from this relationship, we can basically say that P2 is going to be P1 multiplied by V1 by V2 whole power gamma, and V1 by V2 is nothing but your compression ratio. So I'm going to code in that formula. You can see that I'm not at defined gamma, so I'm just going to add that to the input variables. At this point, it is a good idea to check to see if the program actually runs. So I'm going to save the program and I'm going to run it. Okay, looks like we made a small error in line number 10. I've added the unit for temperature by accident. So looks like we have another error. It says that the variable P1 is not defined. Now here I have P as uppercase P, and here I'm using it in lowercase. So what I'm going to do is I'm going to convert this into lowercase so that we have some consistency. So we have computed P1 and P2, and as a sanity check, you can see that P2 is higher than P1, which means our code is doing the right job. Now to compute the temperature in state point number 2, we are going to be using the ideal gas law. Since PV by T is a constant, we are going to say that P1 V1 by T1 is equal to P2 V2 by T2. Alright, so what I'm going to do is I'm just going to copy this formula right here and I'm going to paste it. And if I execute the program, you can see that T2 is also computed. Now let us move ahead and determine the state variables at state point 3. Now state point 3 represents the endpoint of the constant volume combustion process, and hence V3 is going to be equal to V2. And in order to facilitate our calculation, we are going to assume that at the end of the combustion process, the temperature of the charge is going to be 2000 Kelvin. And hence T3 is going to be set as 2300 Kelvin, and this is going to be an input. Now the only state variable that we need to determine at state point number 3 is pressure. This can be determined using the ideal gas law. So what I can do is I can copy and paste this line of code, and if I execute the program, I should get the value for P3. You can see that the value for P3 is substantially higher than P2, which kind of checks out because when the combustion process takes place, the pressure is going to be the highest. Alright, so finally we need to compute the state variables at state point number 4. So the volume at state 4 is going to be equal to volume at state 1. And to compute the pressure at state 4, we can say that P3 V3 power gamma is equal to P4 V4 power gamma. From this expression, we can say that P4 is equal to P3 multiplied by V3 by V4 whole power gamma. So I'm just going to copy this expression and I'm going to paste it and make sure that I add the multiplication sign. And if I execute this code, you can see that P4 is also determined. So now at this point, we have all the 4 state variables. So we can make a plot. I'm going to first open a new figure window, and then I'm going to add the hold on command. And now we are ready to plot each of these state points. I'm going to be plotting them with red colored markers. Alright, I can then copy and paste this and change the state variables appropriately. Okay, so now if we execute this program, we are getting our PV diagram. So now that we have managed to plot the individual state points, we need to think about how to join them. We cannot simply connect them with straight lines because that would be incorrect. Alright, so one of the things that I've seen many people do incorrectly is they would type in something like plot So what I'm basically doing here is plotting all the state points and then joining them by a straight line. So if I execute this, I'm just going to get a curve like this, which is completely incorrect. The constant volume process is right, but then the compression process and expansion process have been represented by the wrong path curves. Now, in order to determine this correctly, we need to make use of two things. First, we know the thermodynamic relationship during the compression process. We need to use that. The second thing is we need to use piston kinematics to determine how the volume changes from the top dead center to bottom dead center. And we'll be doing that in the next video. All right, I'll see you guys. Bye.